Welcome back to the deep dive. Today, we're doing a really focused look, a laser focused look, at one specific piece of hardware, the NTI ST-C5V-L-1000SP high-res VGA transmitter. And our mission, really, is to get into the weeds of how you can reliably stretch those classic KVM signals. That's keyboard, video, mouse over, just enormous distances, all using cabling you probably already have.
Exactly. We're talking about a fundamental engineering problem. How do you get local and remote access to a PC that's up to, 1,000 feet away? That's 305 meters, and this does it over standard CT5 or CT6 cable.
And it's not just a simple adapter, right? This is a whole system.
It has to be. It's a two-unit system. You have a local transmitter by the computer and then a remote receiver where your monitor and keyboard are. It's designed to bridge old tech with modern infrastructure needs.
And when you say old tech, you really mean it. This thing is keeping critical systems running. Things you can't just unplug and replace. We're talking PS2 support for keyboard and mouse.
And that's essential. Think industrial control rooms, manufacturing floors, places that haven't moved to USB for very good reasons. That backward compatibility is its whole reason for being. The local unit has that old-school 15-pin VGA connector and the two little 6-pin mini-DINs for PS2.
Okay, let's get to the core challenge here. 1,000 feet. That is it's about 3 football fields, end to end, pushing a video signal that far over copper. Usually the quality just falls apart completely.
And that's the central tension, right? The trade-off between resolution and distance. That's where the physics starts to get in the way. So while the unit can technically support these, ultra-high resolutions up to 2048 by 1436.
You're not getting that at 1,000 feet.
No way. Not even close.
Yes.
If you want to go the full 1,000 feet, your resolution is capped. You're looking at 1920 by 1200 at 60 hertz, which is still very good, but it's not the maximum.
So what's the deal if you absolutely need that top end, that 2048 by 1436 resolution? What's the trade-off?
You have to shorten your cable run a lot.
Yeah.
You can only go up to 600 feet. It's about 183 meters. It just shows how hard it is to push a high bandwidth analog signal like VGA. Every extra foot makes it exponentially more difficult.
Okay, so this is where it gets really cool. How do they actually do it? How do they keep that picture looking sharp over hundreds of feet of regular network cable? There has to be some kind of active compensation going on.
There is. The key feature is the automatic adjustment for video quality.
Yeah.
And something called color skew.
Color skew.
Yeah. So inside a CT5 cable, the individual wires for red, green, and blue aren't exactly the same length. Over long distance, this means the signals arrive at slightly different times. Without correction, you'd see color fringing or a ghosting image on the screen.
Yeah.
It would be unusable.
Okay, and that sounds like it would be a total nightmare to fix by hand.
It would be impossible. So the unit automates it. It has a mechanism that adjusts for that timing delay. And it's incredibly precise. It can compensate for a maximal delay of 62 nanoseconds.
62 nanoseconds, that's tiny.
It is. And the adjustments are made in these tiny 2-nanosecond steps. You can fine-tune it with push buttons on the remote unit, and it just remembers your settings.
That ease of use is a huge deal for reliability in the field, I imagine. And for anyone managing, say, government or commercial infrastructure, it's worth noting the build quality here. It's a rugged steel box, and it's TAA compliant, which is critical for U.S. government contracts.
Right. They also built in surge protection and something called DDC-to-B support. That's basically the protocol that lets the monitor tell the computer what its capabilities are. It's all about seamless operation.
So when you put it all together,
You have a surprisingly affordable bridge. It lists for about $200 for managing high-res legacy systems over really long distances. It takes about 10 watts of power per unit. And interestingly, the steps say you need a minimum of 100 feet of cable.
a minimum. Why?
So the compensation circuits have something to work with. Too short, and the skew is too small for it to properly correct.
Fascinating. So let's leave you with this. Think about that tiny critical number, a maximum delay adjustment of 62 nanoseconds. What kind of time-sensitive applications or physical layouts might that very specific, very small timing window enable? Or maybe more importantly, what might it prohibit in a modern, geographically spread out system? Something to think about.